by Jason-Hall about signature of spin and charge, signatures from thermodynamics and density measurements. Thanks.
Thank you for coming to such an early talk. And this talk is really aimed for the experimentalists who work on atom microscope experiments. And so I'm grateful that a number of them and their groups are in the audience. Well, I'm also grateful that I think today there are many numerical people doing the computations are here, and I also want to present to them hopefully they will find it a neat problem. The topic is really about the fermion hybrid models, and I think there are a number of. I think the goal for us is to help the condensed methods to resolve long-standing problems and then to resolve a lot of conceptual difficulties which they have been struggling for so many years. So therefore, I was hoping that we can do experiments to answer to determine results and to answer questions with certainties. So some of the questions I would like to answer, or at least address in the talk, is that what are the observable effects related to holons and spin-ons, if there's such a thing, and then what controls the motion of the holes. I think we have heard two talks, one experimental talk, one theory talk yesterday from the Harvard group, and the third question is that, which I'll come to at the very end, is suppose we are able to get to a temperature 10 times lower, say maybe 50 times lower in the two-dimensional hybrid model. Is it possible to see the effect of pairing? And if not, if in the unfortunate case not, are there any ways that we can really determine the pairing, in particular to answer the question whether this model has anything to do with with D-wave superconductivity and high-T superconductors. The talk is based on these work, and basically one of them is on hybrid model, the other one is on the TJ model, and I will convince you that at the sufficient low temperatures, then the two models are the same, and then and a lot of I think a lot of the ideas actually was established long ago by Professor Wang Zhengyi at the Institute of Advanced Studies in Beijing, and he has been working in this direction for many years. However, I think the communication between the co-atom community and the certain fraction of the condensed community is not very efficient, and there's a lot of language barriers. So, but what I will talk about a lot today about the so-called the concept of phase strings, and then is something that is established by him some time ago, and so here is some. I would like to make the point that there is a considerable merit rather than thinking about a two-dimensional square lattice. And let's first think about a ladder. A ladder is something of this form, that you have two legs and then the hopping, and then you can make the hopping here different from the hopping there. Horizontal and vertical are different, and then the TJ model, the hybrid model on the ladder would be this usual form, except that the hopping you can tune, and then the on-site interactions between different spins. And then one can also write the corresponding TJ model. This is understood to be no double occupancy, although I mean, it's deceptive to just write like this, but this means that I'm working on the subspace of the no more than one fermions. And then the question that I'd like to address is that if you have a half-field band and then insert one hole into the system, what would happen to it? And this is the entire talk. The entire talk, or the 99% of talk is about this. And then the message I'm going to convey is also very simple. I'm going to tell you what the exact results are, and the exact results are based on exact diagonalization and also the DMRG result, density matrix renormalization group results. And so they are in principle exact. So then the question is that once we have the answer, could you see some of them are very unusual. Then the question how to understand the collection. I mean, we will see many of them. It's not only one data. So there's a collection of data. Is there any simple way, any consistent way to understand them? And that will be the end of the talk. And then at the end, I'll come back to address the issue of if we are able to go down in temperature 10 times or 20 times, 50 times in the next 10 years, well, can I see pairing in 2D hybrid model? Right. So now, but of course, in doing experiments, then one have to. I mean, let me first address some experimental issue first to do this. But then one really have to create a model with every size field except one of them. But in general, when you prepare a sample, when you do, take pictures, one may not be getting this. I mean, one may be getting maybe sometimes doublons, but now doublons you can, in principle, still get to low temperature. Maybe you can eliminate them, or maybe sometimes you get 2 holes, 3 holes, etc. So I think one typically would have to, you do a lot of experiments, and then you have to select from the experiments that, because every time you take a picture, that you have 1 hole, and then or maybe 3 holes, etc. And then you have to collect, select out from the data that you have 1 hole, and then you average out all the 1 hole pictures. And then by post-selecting the data and also averaging over the post-select data, I think one can then compare with the result that we are going to talk about. Let's see, where's Christy Chu? And then yesterday she mentioned that, well, I mean, at the end it was basically telling the audience, look, don't complain because I do, you say 20,000, something like that. I am sorry, 60 to 80,000. But yes, there's a gain. I mean, if one has to do 10 times the work, but you get 100% of certainty, I think one may be worth it. So so here, let me just tell you about what we found out and just keep showing you the data. So these are the things that one would find. So you have a 2-leg ladder, and put a hole, and then you look at the ground state. And then once see, if you have only 1 leg, then you put a hole in, and then the hole moving around with spin charge separation, then things are very uniform. And then you don't see any density oscillation, etc. However, you have 2 legs, then you see a pronounced density oscillation, as I'm going to show you soon. But if you have 3 legs, you don't see anything. And then you have 1 hole, you see something. You dump another hole, you also don't see anything. And if you weaken the bond, you also don't see anything. We gradually weaken it. And if you produce imbalance, don't see anything. But then if you don't do any of this, just a simple thing, and just put a hole in, then you see oscillation. And the oscillation, and then so I'm going to show you the data. And not only oscillation, and there's a pronounced feature also in the momentum distribution. They come hand in hand. When the oscillation disappears, those features in momentum distribution also disappear. And now, and so why do we care about this? I mean, so there, you can always do some calculation on some system. Are there just details, or would it be able to address questions of principles? And then I hope to convince you, it is the latter. That I think the results will, exact results will shed considerable light on the basic mechanism of the motion of a whole. And the large oscillation, large collection of phenomena has a simple explanation in the so-called phase string picture, which I shall explain, which is the phase fluctuation caused by the spin backflow. And these results are exact, and they can be used to calibrate proposed theories. The physics, although very subtle, is actually very transparent. And the many features can be obtained even by back-of-envelope calculations. And then that is the message that I like to convey. Now let me show you the data. So this is just I think the experts in the audience know how to do all these calculations. I mean, either you do exact diagonalization of the hybrid model, and or you do the MRG, and then this is two-leg ladder. You can do very long chains, and then I think my colleagues have done up to 400 something. And so here is a short train. I asked them to do a short train because at that time I thought that, wow, maybe this is easy to do an experiment, because I think it was I was told that for long chain 200 sites, and you see all these oscillations. Then I asked them, would you be able to see in a shorter chain? Now, how small a chain can you see? So this is the very small chains, only 12 sites, and then 20 sites, 40, and then you can go up to 200. You can still see all these oscillations. The U over T, these are the parameters of hybrid model, which I'm not going to. I think I don't need to explain to the audience. So for sufficiently large U over T, you see these oscillations. And now let's see what happened. I think so early on, and then Professor Wang Zhenyu and his group, and actually for many years, they have done a lot of calculation for TJ model. Now the reason I would come back to the TJ model is that because there is a considerable body of work in the literature by his group and by other people on TJ model, and the discussion I'm going to talk about, say the so-called phase strings, is also based on TJ model. Although it can be generalized, it has a generalization to in hybrid model, but the TJ conceptually it's simpler. We don't have to do that, but this picture is just to show that the two models are the same, but essentially the same. They have the same qualitative feature. Here's the hybrid model. I mean, there's some black curve, and then the blue ones are the TJ, and then one of them are one of them is charge density or particle density. The other one is spin density. And this the people in those studies often plot. This is actually the whole density, that's the holes. And experimentally, we measure particles, and then you just need to invert them. So when you measure particles, and then these are say the spin up, so would be the black curve, and then spin down would be the open curve. And then when you have spin up, spin down, and then you can form the total density. And then so basically you see everything is oscillating. And then the
Are the T's and U's and J's consistent? Because the ratio seems to be very off. I mean, I know the figures agree, but the numbers don't seem to. So on the left side. Right. Yes, consistent. Okay, good. That's fine. He knows the numbers up exactly. I just know the ratios.
who happy to answer the questions? Thank you.
Thank
you very much. Thank you very much. Yes.
This is a two-leg ladder. Is it both legs legs are looking the same?
Oh, yeah. By looking the same meaning.
So what are you plotting here? You're plotting one leg or the
Oh, no, yeah, sorry.
or
That's okay, yeah.
either
No,
leg
no,
looks
no,
the
no.
same,
Yeah,
it
so
doesn't
excuse me,
matter?
yeah. So the density, by density, one means that one's adding the density of both legs and then spin of both legs. So basically, you think, I mean, yeah, that is it. Yeah. So excuse me, yeah. Right, thank you for very much for clarifying a bit. Otherwise, it will be confusing. So basically, when I plot the density and spin density, I mean, I have two legs. I mean, it's just looking up, I mean, counting all the spins.
Just a quick question. The negative density was
No, it's not density. This is spin. Spin end up minus end down. Those therefore, okay, that's the. So now, excuse me. So what happens if we dump two holes in? Now here's a typical situation. For example, if I have one hole, then then this is spin density, and then also the total density. But then once I put in two holes, everything's very smooth. I mean, then again, this continues for arbitrary lengths that you can find. And then now what happened is that if you weaken the bonds like so, I mean, suppose if I change alpha to be very small, and then when, of course, when alpha is really small, then this becomes individually separated. But when you turn it down from 1 to 0.4, then all this oscillation before becomes again disappear. So again, it shows that the oscillation. Well, it just shows you the direction of where the oscillation disappears. The third one is that now I'm going to spin and balance it. Suppose I have more up particle than down particle. I don't know where it distribute, and then they suppose you start out with more up and down, and then again you want so you put in one hole, but the background has more up spin than down spin. This also weakens the oscillations. So there are many directions that one can weaken the oscillations, and then the question is why. The last thing I'm going to show is that if I look at the momentum distribution, then one discover, again, this is for different alphas, and then sometimes it have a peak, but then when there's a peak, and also the charge oscillation disappears. But then when the charge oscillation occurs, the momentum distribution has split into two peaks on both sides. So the existence of the splitting of the peaks come hand in hand with the oscillations. And that's just meaning that this guy is actually mobile and he has a momentum. Questions?
What are the boundary conditions?
The boundary, also, it is an open boundary, so it's a finite chain, and then there's just no more coupling, right? So you can think about a chain that have a T and go to 0. So, right. You can think of hard one, yeah.
Do you require a flat potential, or do you require a flat potential, or does all of this also hold in a crowd?
The calculation were done in flat potentials. We can discuss the reason. I don't think it will change very much with and for the physics reason we don't talk about. Yeah. But it can be done. Yeah, we haven't done the harmonic potential. So So I would like to. So these are numerical results. I mean, we are, and the question is that is there any physical way or analytic way to understand this phenomenology? And I would like to present an explanation. I would not call it a proof, but I would think it's very convincing. And then the first two are vigorous results. And then the first result is on the so-called Marshall sign, is about the nature, the ground state of an antiferromagnet. The second thing is a formal result about the propagator of a hole in a antiferromagnetic background. The result is this result is the starting of the idea and the picture phase string. The result is, as I say, you see, is a formal result, and it tells you about where the spin black hole comes from. It is not computationally convenient in the sense that if you still use it, you might have still run the program. But on the other hand, but just making a simple approximations or a simple simplification for this propagator formula, one can immediately gain and then that formulation amounts to the so-called saddle point approximation, and then picking out the dominant contribution. And then once you present the whole collection with a dominant path, and then the dominant path have a phase associated with it, then one can actually explain everything that I mentioned to you about. So I first tell you about the two exact results, and then I'm going to tell you how the exact result explains how this result after the simplified picture can be explained, can explain the previous pictures results. So the first thing is about the so-called Marshall sign, and it is written in presented in the paper by Marshall in 1955. During that time, there's a beginning interest of quantum spin models, and in the paper he credited the argument to Rudolf Peierls, and the argument is follows. So I can, by the way, where is Christy? Yeah, right. These symbols are Harvard symbols. These symbols are Harvard symbols. I saw it in the picture yesterday. I find it actually much easier to see than the up and down arrow. So to the Harvard credit. So no matter how the Marshall, so the point, actually the important contribution is that even though I don't know what the ground state is, I can still tell you some relation about the ground state. And he's saying that now I can always expand any state in terms of the spin. When you can write down spin bases, and then there are zillion two of n terms, the zillions of them. And by the way, I also want to mention that these up-down pictures are very deceptive in talking about antiferromagnets, and can get people into great trouble because the system is not like this. The system is, and then therefore, Richard knows very well. There are some work by Anderson that show that antiferromagnet can be written as a distribution of mixed RVB bonds, and then for different distribution size, and they average them. If the range is long enough, then you get antiferromagnet. But in that formulation, every single wave function is completely screwed up. It's not up down like this. So all it says is that there are a lot of up down correlations. But the very fact that even in one dimension, the depletion or metallization is 70-something%. It means that this is a very bad picture. So there's a lot of mixture. Even though I flip a little bond, and then the tradition will say, wow, it's very bad. No, it's not very bad. There's a lot of them there. And so there are zillions of them. But Marshall is saying that there's some relation to coefficient, that if I flip any spin, any pair from here to there, I change the sign. So Marshall is saying that the coefficient, first of all, are real. The secondly, then when you flip them, you change sign. So it must be something like this. If you fix this sign, then the rest of them, you have no choice. In this case, if I flip this spin, then I go from plus to minus. And then here I flip this spin plus and minus. If I flip two of them, then would be plus again. That is the Marshall sign. Now what would happen if I create a hole over here? When I create a hole, I say I take the previous picture, I create a hole. But for this guy, it goes 0. Why? Because here this is a down spin. If I kill off, then I can then I kill off this guy, and then so that's why I have contribution here. Now what happened that now if I consider the other state, that I have moved the hole, I create the hole, the next, say, one step down, and now it kills the spin. But then for this, because I've exchanged this spin, and then this become non-zero, but all the other ones 0. Now I don't mean this picture. Do not mean to say that when you add one hole and then there's only one coefficient that will match together. There are zillions of them. So actually there I mean, somewhere down here, then the other term can match this term, which I haven't written down. In fact, there are 2 to the n terms, and then so basically create a hole. You can zoom, you can produce a lot of the holes in each component, and then everyone propagates, and then you collect them. Yeah, then through here, and each time you collect, each time you proceed, say hop to here, you change the sign. So basically, hopping from one side to the neighboring side will involve a sign change. And then the spin and the sign change represent the spin black flow. In other words, a spin black flow must involve a Marshall sign change. And in addition, one had to need to sum over all the spin configurations. I mean, there are many of them. So, questions, please. Oh, the original proof is yes and no, but it would take it would take a digression. No, it's actually a clever observation. That. Already?
Yes.
Are you serious? Oh, my goodness! I don't have to stay up so long. Okay, I didn't. Okay, well, I apologize for the I didn't know. So this is done by Professor Wang Zhenyi, and say, well, now I'm going to look at the propagator. Sorry about the speed of my English. So he's saying that, well, I'm going to look at the propagator, and then the propagator, now you can rewrite it like this, and this is the on-site thing, and then the propagate. And then so when you look at this, you discover that I have this collection of wave function come in here, and then this is a J, which is a local, and then zoom, it makes up a lot of spins, and then every time, and then you mix up a new configuration, and you propagate one time, and then again you mix up, and then you propagate. So this is the process of propagation, and he found the final result that he can show that this is the Green's function can be written in this form. That there is a it cannot be 5 minutes, but anyway. So something is the positive, and then there's a collection of changed Marshall signs, which is these are really just all plus 1 minus 1, and depending on the path. So here's the general because I screw up with my time. So if I propagate from, there are many different paths from 1 to, so conceptually something like that, many paths from I to J, and for each path there's lots of spin oscillations, and then like this, and then they can but each one of them associated with a set of spin flip, because whenever for any spin configuration, when the hole moves around and you see it encounters a exchange with let's say with upspin, and then or with a downspin, and then each time then there is a change of sign, and then that is so this collection thing actually the number of downspin. You can make it upspin also, but then let's say a downspin. Well, with a -1. So that is the concept. Now the question is that this although formally exact is very inconvenient to use, and although it has a nice picture of the spin stirring, and then so now we are going to make a simple approximation saying that among all these terms there's one dominant term. Well, there's one dominant for any given path. There's one dominant spin configuration, and then it will give me a average. The phase, and then average of the phase. So I replace all this by this small amplitude. Now, once you do this, then the whole thing looks like a wave function. And then the wave function would now looks the following. That now you can it's very fast now, and because so at long distance, and then for example the.
Just relax.
Are you realizing making a mistake?
2 minutes.
I see.
Please don't blow my eyes with your pointer.
I'm sorry. Yeah,
It's not my fault.
I did this many times. Okay. Since we are all friends, and with Francesca's kindness, I'm going to I'm going to because that's one more thing I need to say, and then you say so. But even if I assume there was a one dominant path along here, and then there's a phase, and then phase is again is given by the Marshall sign, which is a number of downspins. But now I can write the number of downspins, this total number of downspins, in terms of something like this. Is the length of the path versus basically the average number that you encounter spin flip. So this turns out to be key quantities that along a path, how often it's almost like a scattering process. In a path, then how often you exchange with one of the spin species, and this controls basically all the periods that we're going to talk about. So with this picture, then for example, then I can rewrite this in terms of this fundamental quantity plus say this is length times the density of a spin flip. But then because of this property, so it looks like a wave. Now, however, because this property that two of this is just a number, like that two of this number is even, always one. That means that either I of s is the same to either minus I of s. So therefore, if you have this wave, you also have this wave. And then now p is equals to, say in this case, you identify the momentum is equal to this. Here, the momentum you can identify to be 2 pi minus this quantity. So the whole thing is symmetric around pi. Let me now show you. Oh, sorry, here's a density oscillation also. We can go forward. And the density oscillation, similar calculation shows that the oscillation is equal to 2 kappa. Oh, sorry. Kappa is actually related to p. So sorry about that. So what happened is that if you look at the momentum distribution, this shift, that shows that there are two peaks. Once you have this p is not 1, and then one can also show that this shift is related to the density oscillation, and these are the data, so they come in hand in hand.
So Jason, doesn't this argument say that in the 1D case you'd get your oscillation, the single line?
No, because in the 1D case you don't have a phase string, so you don't have a phase. That phase string picture is due to the interference.
How about the 3-leg?
Three-leg, you don't get it. No, I'm going to explain all of them. Feature. That's why in odd number that you don't see that. Right? So now I'm going back to the beginning. I'm going back to just the oops, sorry. There's a very. This give me. Just please. Yeah. I'm going to go back all these pictures. Why now in one leg? Then because like here the reason that it's not enough time. The reason that I get an oscillation because there are different paths I can interfere, and that's why I have this oscillation. In 1D I don't have this. I can go from here to there one path. Now why would I don't get 3 paths? Now one can understand it from the following basic ideas. Basically you pair up both of them. Experimentally, numerically, you don't see any oscillation. So basically, the rule is that we have 3, and you pair up 2 of them, you end up with 1. And then now, so 4, you also see oscillation, but it's not as pronounced. Now, why do I don't see the 2 holes? What happens if 2 holes? You can also show the phase string of 2 of them cancel each other to a large extent. Basically, if you separate distance and they can move around, there's no effect of phase strings. Because the end cancel all the fluctuation around and cancel each other. So so this also shows that 2 holes, the phase string effects, and then there's some phase strings around there that actually ties the hole together. And then now you're weakening the bond. Now you weaken the bond, and basically the whole thing becomes opposed to the independent objects. And then in this case, you can actually show that the whole thing actually hops around and then as a whole. So therefore, like again, the motion is for this object is coherent. Now, raising the reason that you don't have the oscillation by raising the spin imbalance is that when you polarize a system, then of course you lessen singlet, so therefore it's also weakened. So everything can be interpreted as a consequence of the phase strength oscillations. So I'm 99% done. I had mentioned very early on that I would mention a comment on the prospect of whether, suppose I can get the temperature 10 times or 20 times, 30 times lower can I see spin pairing. And that is related to the question of whether this model, how much of it is really responsible for high TC superconductors. Now the following is done by my colleague, Bill Pudiker, who is an expert in high temperature serial expansion. These are the result from high temperature serial expansion up to 12 orders. And that it's the longest series in TJ. And then he told me that the calculation in hybrid is much more difficult, but he's pursuing. I just want to point out one thing that I think Francesca has practiced Kung Fu before. That now this is the spin correlation length. Even down to T over J for sorry, this is very low time, so they use TJ model. It's basically 0.1 T in our this is only about 1 or 2 lattice spacings. If you go down to the projection, is like go down to 10 times lower, then you don't have you may not be get much bigger. So if, ladies and gentlemen, the correlation length, if you after you work for pairing, not for the spin correlation, for pairing turns out to be a few lattice spacing, you don't see it would be hard to see any pairing correlation in the same magnitude as spin correlations. I think the one way to overcome it is actually have several layers. I mean, 2 or 3 layers. Then I think also maybe that some fraction of a high TC people believe that the reason that you have superconductivity is actually a couple layers. Once you couple them, the correlation length can be expanded considerably. Thank you very much.
Thank you to you. I think we have time for questions.
Oh, really? We do?
Yeah, we do. You see?
The last slide behind you, is that for infinite two-dimensional lattice?
This one, sorry, this one is for infinite two-dimensional lattice. This one is for this slide is for high temperature serial expansion, which is designed for infinite lattice.
So it's not for that anymore.
That's not too late anymore. Yeah, this one is completely separate question.
Yes, please.
So going back to the idea that if I weaken the bonds, I stop seeing the oscillations. Is there a critical bond?
Yes, there is. Yeah. I mean, I think there is. By that time, but we have alpha 0.25, something like that. So, yeah, right, that's right.
Yes, please.
So what role does SU2 symmetry breaking play for the phase string story? Because the latter probably does not break it, right?
Right. So my understanding is that for example, I have labeled the phase strings as label the number of particles up, but then you can also label the number of particles down. I think, but so because I think. Other aspects I do not know yet, but yeah, but that is so yeah. But I think it can be. Oh, okay. Let me. It has been a very difficult process for me to understand this set of paper, and the reason I bring it to is not because it's related to my work, because I do think this picture has some merits worth considering. And as I say, the majority work is done by the group, and I think, and I can complain to them, beating them up, saying that you have to speak in the language that is useful. And I think that we can, I mean, our community can help to make things as simple as possible, basically. Right? Yeah, whether all the calculations are done at 0 temperatures. What's your name, please? Yeah. The first part on the DMRG on the two-leg ladder are done 0 temperature. So therefore, temperature effect is very important. The last one I mentioned is done final temperature. You can actually see I cannot go down to 2. Right. Yes. And then,
For the first part, if you do exact diagonalization, where you see the distribution of eigenenergies changes significantly after you add in a whole. I just curious.
you can get the spectrum. You can, I think the problem for exact ionization is that one cannot do too long a chain. And then I think you know very well how long it can, it can do. But it has advantage. It can do thermodynamics, and then my understanding maybe 8 to 10. So it's pushing there, and one can do some of the things that you mentioned, especially look at thermodynamics. But that is very important, and I don't expect the thermodynamics would change. Well, at least for range temperature, change very much because the bulk is there's a gap there actually.
Okay, so thanks a lot again.
Thank you very much, Francesca.